So we can find relative extrema using the second derivative. The second derivative test helps us to find relative extrema, but I really wouldn't use it unless I don't need to determine increasing or decreasing. Again, this test is used mostly when you do not need to determine increasing or decreasing, and you only need maxes or mins. Let f be a function such that f prime of c equals 0, and the second derivative of f exists on an open interval containing c. If f double prime is greater than 0, then f has a relative minimum at c f of c. Well, remember the second derivative tells us about concavity. So f double prime being greater than 0 means f is concave up. So what does that look like? That. Similarly, f double prime less than 0 means f is concave down. What does that look like? This. So you put this with the concavity, this being a slope of the function is 0, so it's a horizontal tangent, and that creates a min, a relative min, or a relative max. Using the second derivative test to find the relative extrema, justify your answer. Now, I put this problem on note card number 37, so you can compare your answer to that. First, we're going to see if there are any critical numbers. So first, we're going to find critical numbers. G prime is what we need, 3x squared minus 3x. That looks like what we have. Set it equal to 0 since there's no places this doesn't exist, and we can factor it and get 0 and 1. Two critical numbers. These are our two critical numbers. Now we're going to figure out the concavity. So step 2, find the concavity. So the concavity is our second derivative. G double prime is 6x minus 3. Where is it positive? Where is it negative? I don't care where points of inflection are. I want to know what is happening at these critical numbers. So not just find the concavity, but find the concavity at the critical numbers. That's where I want to do it, at the critical numbers. So G double prime at my first critical number, 0, is, I don't care what value, what sign is it? It looks like it's less than 0, it's negative. Therefore, G is concave down, looking like this, and that means there is a relative max at x equals 0. Let's plug in the other critical number, 1. G double prime of 1 is 6 times 1 minus 3. 6 minus 3 is positive. Therefore, what is G? Concave up, looking like this. At a critical number, what does that mean? Relative min at x equals 1. Finding the relative extrema, we found where they're located, and then remember you plug it in to find what the y value is. So G of 0 is 0. G of 1 is, with 1 plugged in, 1 cubed minus 3 halves 1 squared. It looks like we get negative a half. So the relative max is at x equals 0. It is 0. Here it is negative a half. That's how we can use the second derivative test. Let's look at it in a couple different ways. If f has a critical number at x equals 2, so they're telling us the critical number, the second derivative at 2 is 3. Who cares that it's 3? The fact is that the second derivative is a positive number. So that means we have a concave up graph, concave up, f is concave up, at a critical number. What can we conclude about the function at x equals 2? That means there is a relative min. So therefore f has a relative min, f has a relative min at x equals 2. That's what we can conclude. Here's another way to look at it graphically. Using a graph of the second derivative, what's happening to the function at x equals 1 if the second derivative is 0 at x equals 1? This is telling us that there is a critical number at x equals 1 on the graph of f. Well, at 1, here's where x is 1. This is the y-axis, the x-axis. Here's where x is 1. This is a graph of the second derivative. And look at where the second derivative is at x equals 1. The second derivative is below the x-axis. The second derivative is less than 0. the second derivative is negative. Therefore, and this is at x equals 1 that we're looking, therefore f is concave down. What does that look like? This. At a critical number, therefore our conclusion is that f has a relative max at x equals 1. That's the second derivative test.